So here we are pulling things together from Explain Part 2 today. Asked you to have that ready to go. We did start the period with retake options for quiz number 2. So if that's something that you need to do and you're watching this at home outside of class, message me right now, hey, I missed the retake Friday. How can I do that? So you got to shoot me a message and let me know. And we'll figure that out. Otherwise, we jumped right in with some practice from yesterday's discussion. So we talked through what nucleosynthesis was yesterday, specifically thinking about what it is, what's happening to elements, and what is being made through this process of nucleosynthesis. So we said essentially it's a fancy word for fusion, right? We have two elements that are existing and being pulled together by that force of gravity. And as they're pulled together, they fuse or combine into one. And as they combine, we're seeing two things come out of that combination. One is a new, heavier element, right? Made of more stuff. The example we looked at yesterday was hydrogen into helium. And the other output that we get from this combination of two elements is a level of energy. So energy is released as elements combine and fuse into one. And so we said this initiated with the Big Bang, which of course 14 billion years ago, when we had all that hot energy, strong gamma energy, kick-starting this expansion. And so we started seeing these little tiny particles combine into our building block elements. And those very first elements are, of course, hydrogen, helium, and lithium. And we said those are those initial building block elements because of their size. They have a really simple composition, right? They're so small, just a few particles needed to make helium, a few particles needed to make hydrogen. Oops, I mixed those up. Hydrogen, helium, right? And then these two can easily start to combine to make lithium. They're so small, gravity doesn't need to be super strong to pull them together. So that's what we recapped yesterday. Thinking about your part 2, you started seeing the stages after Big Bang. Because just out there in the universe, we have enough energy to make these basic, simple elements, but we can't quite get to the next level because we don't have the best levels of temperature, pressure, and gravity. We need a star to get us there. So looking at your notability, we're going to summarize our part 2 here, starting by writing a few notes on our picture like we did yesterday, and then we'll come down here and put a few bullet points in additional information. So again, you should already have your part 2 questions complete. So here we are, stellar nucleosynthesis. Stellar simply means star. So this is fusion or nucleosynthesis that happens to every single star. Okay, all stars are going through this stellar nucleosynthesis, and currently our sun is in this basic stage. What we're looking at here is a diagram of a star like our sun fusing hydrogen into helium all day, every day. You might remember we said the sun is 5 billion years old. It's been burning this fuel of hydrogen for that long. And as it's burning hydrogen or fusing it through the process of nucleosynthesis, it's creating this outward pressure force. So this pressure is the out force, and it's the force coming from the energy due to fusion. So fusion is creating this outward pressure, where gravity is, of course, the inward force, and we know gravity depends on mass. So the bigger the star is, the bigger the gravitational force. That's our learning target 1 coming back. And so what we read about in this first section of part 2 is how important it is for those two forces to stay balanced. Gravity and pressure, or that energy from fusion, must stay balanced in order for that star to maintain. So what that means is the star will continue doing what it's doing as long as these two forces are equal, right? They have to stay balanced or equal. As soon as one of those things becomes more powerful, the star really changes. Of course, if gravity increases, if this becomes the bigger force, the star will collapse and be pulled inward. If the pressure force becomes the bigger force, then the star will expand outward. So those two need to stay balanced for the star really to maintain and stay in its stage. So again, our sun is in this stage right now. It's been burning hydrogen from its outer layers for 5 billion years, and it will continue to do burning of hydrogen for 5 billion years. That's how much fuel it has left. So that's our first bullet point of the day. We put it up here by this really descriptive picture. We're going to add our last few bullet points down here in additional information like we did yesterday. So go ahead and scroll yourself down to those. This is the bullet point we already recorded, so we're good to go here, right? So we're thinking about, well, what are these stages then? So the first stage that every star starts at is the stage known as main sequence. And like we said, this is the stage our sun is now. Oh no. This is the stage our sun is in. This main sequence stage. It's burning, like we said, hydrogen into helium, maintaining that balance of inward gravity to outward fusion all day, every day. And that's able to do that because this is not a supermassive element, so it's not creating too big of an outward force to counteract that gravity at this time. So a star can really burn in this initial stage for a long period of time. And it will continue to do that until its initial source of energy runs out. So eventually every star in this main sequence stage will run out of its fuel, which is hydrogen, and the next element will then take over as its fuel. So eventually, as the star runs out of hydrogen, helium will become the brand new fusing element into, you guessed it, more massive elements. Now, as our star continues and begins to fuse helium, it's creating these more massive elements such as carbon, nitrogen, and iron as it becomes part of the red giant stage. Looking at the name, you may be able to tell it will become more of a reddish color, cooling down, and grow extremely large. As the fusion ramps up, these elements are kicking off more pressure and pushing those outer layers outward for a short amount of time. Eventually, as the star starts to become overcome by these more massive elements, gravity can take over and bring the star back to a smaller size. But again, all the while it's keeping that balance, allowing the star to maintain fusion. From here, our sun is going to go one direction, but stars more massive than our sun will continue to fuse elements up to iron. on the periodic table. So it will continue to combine element after element in the fusion process, eventually reaching iron stage. And like you saw in the reading, the more massive these elements become, the harder it is for the star to fuse them together because they're more massive. It's more work. So when we look at this visual, and the reading talked about this too, it's saying it can only fuse into iron for a very short amount of time before the star really gives out. There will no longer be an outward force from fusion, and that gravitational force takes over and the star implodes. It comes inward before it explodes in the supernova stage. This is your final bullet point down there in the additional comments, saying that more massive stars will supernova, sending these elements heavier than iron out there into the universe to then create other things. They can create new stars, comets, asteroids, and planets. It's thought that our solar system is created by the remnants of a giant supernova, stating that all these more massive elements that exist on Earth today and around us now only have come from the center of those supermassive stars and the cloud of a giant supernova. At this time, you should have all your additional notes filled in for part 2. If you need to go back and get any of those 4 bullet points, you can certainly do that in the video. You're now rolling on to part 3. You got a short section to finish up and get that submitted ASAP.